Hello and welcome to week 9 of the course Introduction to Semiconductor Devices by Professor Naresh Kumar Imani from IIT Hyderabad. The course ID is NOC 25E92 and this is the problem solving session for week 9. I am Mayank Goyal, a research scholar at the Department of Electrical Engineering, IIT Bombay. The details for this course is being taught by Professor Naresh Kumar Imani, who is an associate professor at the Department of Electrical Engineering, IIT Hyderabad. The course plan for this week is long channel MOSFETs, energy band diagram, and qualitative understanding of MOSFET operation, IDVD and IGVG relationships, square law theory of MOSFET, subthreshold slope, performance metrics of a MOSFET. The, these live sessions are happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. First, we'll do a recap of this week's lectures using the slides provided by Professor. First, some historical perspective regarding transistors. So, the principle behind field effect transistors was first patented was patented by J. Linienfeld in 1926. His concept was using a metal, aluminum oxide, and copper sulfide. In the 1940s, the theoretical contributions for transistors were made by Shockley. Then in 1947, Bardeen and Brattain invented point contact transistor. You can see in this picture what a point contact transistor look like. So this had a germanium base. This point contact was emitter and this upper part was collector. Then in 1959, Atala and Khan demonstrated MOSFET, and then in 1961, first monolithic silicon IC was invented by Noyce, and this is the first monolithic IC by Robert Noyce, who was employed in Fairchild in 1961. So the Fairchild later on renamed itself as Intel. So there are generally two types of transistors that we study. We study generally two types of transistors: BJT, that is bipolar junction transistor, and FET, that is field effect transistor. So in BJT there are BJT has a very simple structure. It is basically just two PN junctions. It can either be NPN or PNP. So you can see here. So this is your N N side in which you do a P type doping, and in that you do an N type doping again. So this outermost is your emitter. This middle one is your base, and the bulk one is your collector. Similarly, for PNP, the middle one base is the N, and emitter and collector are P types. Field effect transistors have slightly complicated geometry. So there you have a here you have a P type silicon on which you have grown in oxide, and then there's a metal which acts as a gate, and then you made two n plus type contacts here which act as your source and drain, and this is an N MOSFET because this middle part represents an NMOS. Similarly, you can have a P MOSFET where the middle part represents a PMOS. So it has, N-type silicon, you have instead of P-type silicon, you have N-type silicon as your base, as your semiconductor, and your source and drain are P plus highly doped P-type P doping. So this is side view and top view of how it looks like. So this yellow portion, and then on top of that you make your metal. You on this highly doped silicon you deposit metals for making contacts, and this middle part is covered by your gate metal. This is how it looks in a 3D view. So you can see your substrate is P type here, and on that you have grown an oxide which acts as your gate dielectric, and then there's a polysilicon gate, and on that polysilicon gate you have a gate metal to act as contact, and then on left and right you deposit a you do a highly doped opposite type, that is N. For P type substrate it is N plus, which act as a source and drain, and on top of that there are metals for taking contacts. So the whole thickness of this re- doped region is in few nanometers, not very deep, although the substrate is in micron. The thickness of the substrate is in microns. So MOSFETs act in two different modes: enhancement mode and depletion mode. In enhancement mode, which is represented by this symbol, where so this substrate itself can also act as a contact, which is known as substrate or body contact. This is used to modulate the whole operation of the of the MOSFET device. Hence, a MOSFET is generally three terminal device, but including gate, you can call it a four terminal device. There is gate, source, drain, and body contact. So in an enhancement, and this is how the symbol is represented, where the source and drain are connected, and the gate is parallel to it. It is to represent the oxide oxide insulation between the gate and the source drain, and the body contacts goes to the middle of the source drain. In enhancement type, if you by breaking this up, you show that it is being enhanced. So you can see in enhancement type there is no connection between the source and drain, but in depletion type there is a connection between the source and drain by default, a very thin connection between source and drain, and hence in the you can see in the depletion type MOSFET there's a there's a solid connection between source and drain shown here, where here is broken connections are shown in enhancement type MOSFET. So how an enhancement type MOSFET works is that when you apply a certain gate bias, this this MOS cap this MOS region goes goes into inversion region, and that creates an inversion n-type inversion channel here, which connects the source and drain. Uh, Now in a depletion type, what happens is that there's a source and drain by default. So when you apply gate bias, this this goes into this goes into whole accumulate this goes into accumulation, which causes this n-type n-type channel to disappear due to hole accumulation, and the connection between source and drain breaks. So an enhancement type MOSFET is off by default, and by applying gate bias, you are turning it on. You are making the connection between source and drain. A depletion type MOSFET is on by default. There is by default a connection, and by giving a gate bias, you are breaking that connection and turning the device off. That means no current is passing between source and drain. So first we'll talk about subthreshold mode operation of a MOSFET. So we learned that in a MOSFET, it goes in when the channel goes into inversion. Then channel when the MOS goes into inversion, then a channel is formed between the source and drain to conduct. But what happens before the channel is formed? That is before threshold. So in ideal condition, before threshold, the current will be zero. So if you draw an energy band diagram in this cross section, it will come like this. So where your source and drain are highly n-type doped and your channel is p-type, so it will show like this. And as you apply a gate gate voltage, this channel shifts below such that it comes in the same line as the source and drain, and that is what's called your and that is called a threshold region. So before that, due to this barrier height, ID should ideally be zero, but due to thermionic emissions and all, in practical cases, ID is not zero in subthreshold region. But as you apply VG, this barrier starts reducing, and more and more thermionic emissions are possible, causing the ID to be exponentially proportional to VG in the subthreshold region. Then we come to linear mode operation. So what happens when VG becomes greater than VT? So when VG is greater than VT, a channel is formed here. But when VDS is zero, that means there is no bias between this and this. Then obviously ID will be zero. The current across this channel will be zero. But when this when there's a small voltage applied between VD and between VD and VS, that is VDS, then it comes into linear mode, that is the MOS. This channel is acting like a resistor and it is exhibiting linear IV characteristics, and this and the slope of this characteristic depends on a VG value. The higher the VG value, there will be more electrons more electrons in this channel. That means the resistance will be less, and hence the high slope will be higher. Next we come to saturation mode operation of a MOSFET. Next we come to saturation mode operation of a MOSFET. So in this case, when you apply a higher VDS, uh, so what happens is that this change between this 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 difference between VD and VS, that changes the voltage drop across this channel, and at a small region the inversion charges in this channel are uniform when VDS small, but when VDS becomes large, the inversion charges start seeing the effect of this VDS voltage drop, and the density of inversion charges becomes proportional to Vg minus Vx, where Vx is the voltage drop, and as VDS becomes equal to VGS minus VT, then this Vx becomes such that your Q inversion becomes almost negligible. So there are no more inversion charges present for conduction, and hence your current saturates, since it can't increase any further due to non-availability of any more electrons. And hence after VDS crosses VGS minus VT, you will see a constant current, which is called saturation mode current. And that happens because at this region, at your VDS, at your VD region where you are applying your bias, the the inversion charges become zero, as uh, the value of VDS completely offsets the value applied on the gate, and reduce and changes this, and this is called pinch off region because the charges here are now pinched off. That is, they're blocked by this VDS. So when you plot this combined linear mode and saturation mode, this when you put you do IDVDS, you will see that. So first there's a linear region and there's a saturation region, and if you increase VG, the linear region will have a higher slope, so it will go higher. Moreover, the pinch off region is proportional to Vg minus Vt. So since Vg is higher, the pinch off region will be further ahead. So this saturation pinch off or saturation Vd is also higher. So hence the net saturation current at this higher Vg is also higher. Next we will talk about IV characteristics in the linear regime. So we are talking about very small VDs, that is 50 to 100 millivolts. Now VT we can calculate as, we know, 5 ms minus Qi by Cox minus Qd by Cox plus 2 phi f. This is how VD is calculated. So from this you can calculate your Vg, which is equal to VFB, that is Qms minus Qi by Cox minus Qd plus Q inversion by Cox plus 2 phi f, that is Vt minus Q inversion by Cox. From there you can calculate your Q inversion, which is minus Cox Vg minus Vt. So that is, your inversion charges are proportional to how much excess Vg you have applied compared to Vt. From there you can calculate your current, which would come out to be Id equals to Cox Vg minus Vt into WL by tau. So we are talking about linear regime here. So we are not considering the effect of Vd right now, effect of Vd on Q inversion right now. And tau we can calculate by as L by V, that is L by mu E, or L square by mu L square by mu VDS. So putting that in this, we get our drain current equals to mu Cox W by L VGS minus VT into VDS. And if we do dimensional analysis here, we find out that the answer is, indeed comes out in amperes. So this checks, the dimensionality checks out in this. And if you calculate the resistance for this, that is VDS by ID, it will come out to 1 upon mu Cox W by L VGS minus VT. So you can see, as you increase VG, your R will reduce, and hence you will have a higher slope in IDVD. And for and when VGS is equal to VT, your R becomes, this whole thing becomes 0 and R becomes infinity, and hence in ideal condition, at threshold and below threshold, your current will always be 0. Next, to calculate our saturation current, we make some approximations, that is square law theory, that is we take gradual channel approximation. So we make the approximation that our inversion charges q inversion qi inversion changes gradually across the channel. So they are changing very s- they are changing very gradually across the channel, and this implies ex, that is field along the channel, is much smaller than ey, that is field across the channel. And this is a valid assumption for long channel MOSFET, that is when the since we know invert and this SI this our gate dielectrics are in nanometers, so are the so the vertical field is very very high, but in long channel MOSFETs the channel length, that is the distance between source and drain, that is very large compared to our dielectric thickness. So hence the the field across the channel is very small, and hence GC is valid for long channel MOSFETs. Due to this, we can simplify this from a 2D problem into two independent 1D problems, which we can solve independently. For this to work, we neglect the leakage current through the oxide, and we also assume that the carrier mobility in the channel stays constant. So from this theory, we can calculate the pinch off region, that is the point when the Q inversion charges become zero at this point. So we if when we do that, we get that this becomes zero when VDS equals to VG minus VT, that is at VD sat, and when VDS becomes greater than VD sat, this value will shift further to the left, and it will reach zero. Inversion charges will reach zero much earlier. And when Vg is less than Vt, then inversion charges are not formed at all. So by applying this theory, we can calculate current as Cox Vg minus Vt minus Vx WL by tau, and then we put tau here as L by V, which is L by mu dVx by dx. When we put that here, ID equals to mu Cox W Vgs minus Vt minus Vx Vds by Vx dx, and we can then take dx here and integrate over the channel length, that is 0 to L, where L is your the length of the channel, and we integrate this also over Vx, which goes from 0 to Vds. So when you solve this, this comes out to be your total current equals to mu Cox W by L Vgs minus Vt into Vds minus Vds square by 2. So this now becomes your equation for current. Now you can see when for small VDS, this this part of the this part of the sum is very very low, and this can then be neglected, and my current just becomes VDS minus VT into VDS, which was the formula we got for the linear regime. So this th- this gives us the linear regime approximation, and when and at pinch off VGS minus VT becomes zero, so we are only left with, so when VD is greater than VD sat, VGS minus VT is so then so VD sat is your VGS minus VT. So at VD sat value, you can replace this whole thing by VGS minus VT, and if you do that, you will your current comes out to be ID equals to mu C ox W VGS minus VT whole square by 2L. You can see here the current is now no more dependent on your VD, so it is becomes a constant value for all or VDs greater than VDS, and this is your saturation current. If you calculate your resistance here, it comes out to be mu C ox W by L, and this is called a transconductance parameter. So now we do an example problem. The parameters of an n-channel silicon MOSFET are mu1 equals to 650 centimeter square per volt second, Tox equals to 8 nanometer, W by L equals to 12, Vt equals to zero point 0.4 volts. If the transistor is biased in the saturation region, find the drain current for VGS equals to 1.2 volts. So first you calculate your Cox, which is epsilon Ox by Tox. For SiO2, we know epsilon Ox is 3.9 to 8.5 10 power minus 14. T we have given as 8 into 10 power minus 7 centimeter. So our Cox amount comes out to be around 440 nanofarad per centimeter square. Your W by L ratio is given as 12. That you can, and we know our we are in the saturation region, so we will use the saturation region current formula. ID equals to mu Cox W by 12 VGS minus VT whole square. Now all the values you know, the mu is 650, Cox you calculate as 440 into 10 power minus 9, W by L you are given as 12, VGS is 1.2 and VT is zero point 0.4. You put all of that values, so the ID will come in the in the ratio in the order of hundreds of microamperes to few milliamperes. Next we talk about NMOS and PMOS IV circuit characteristics. So till now we were studying an NMOSFET device. So these are the calculated IV characteristics for an NMOS device with 0.25 micron CMOS technology. That is, your W is 10 microns and length is 0.25 microns. So you can see here for VG1, your saturation comes very small, and as you increase your VG, you can see your saturation current increases exponential as a square law, and you can fit that fit your pinch off regions on a square axis. That so the pinch off region is VD equals to VGS minus VT. So you can, when you plot that here, you will see it falls on a square line. as you can see here, the values are not directly jumping from your linear to saturation region. There's a there's a transition between your linear to saturation where the current is non-linear, and that is a much more realistic picture compared to a direct jump from linear to saturation. Now for an NMOS device, you see that your VDS is positive and your ID is also positive, so it works in the first quadrant, that is where V and I both are positive. And as you increase your VG, your current increases. For the PMOS device is exactly opposite to your NMOS device. So here you apply a negative drain voltage, and the current you get is also in negative is negative. So this works in the third quadrant where both your current and voltage are negative. And here what you see is, as you as VGS goes more and more negative, the current increases in value. So everything is reverse compared to a NMOS FET. Now we talk about body effect. So we said that the we can also consider a contact on our substrate, which is called body. So what a body does is that it applies a field over the whole device. So change your when you put a negative voltage on your body, then then a whole band will shift up, and it will and therefore it will shift the value of VT. So this can be calculated as VT equals to VT equals to VT naught plus gamma under root of 2 phi f minus VBS minus under root of 2 phi f, where this gamma is called body effect parameter. Now, what is a good MOSFET? So MOSFET is generally three terminals. In an NMOS, so ground your source here. you apply your you apply your supply voltage on the drain, which goes from 0 to VDD, and you apply your control by voltage on your gate, which is VGS, which can also go from 0 to VDD. In a PMOS, instead of ground, your source sits at a VDD voltage, and your gate voltage then goes from 0 to VDD. And so when we are talk in terms of In terms of IV characteristics, we always talk about voltage with respect to source. So that means we talk about VGS and VDS. That means voltage, gate voltage respect to source, and drain voltage respect to source. So in this case, our source is grounded. That means the voltage at source is zero. So my when VGS is VD, when my gate is at VDD voltage, that is VG is VDD, then my VGS is VG minus VS, which is VDD minus 0, which is equal to VDD. So in this case, my VGS is equal to VG and my VDS is also equal to VD. But in this case, the voltage on the source is not 0, it is at VDD. So when I apply a 0 voltage on my gate, then my VGS comes out to be 0 minus VDD, that is equal to minus VDD. And my when I go for and when I go to VDD equals to 0, when I go to VG equals to VDD, then my VGS becomes VDD minus VDD 0. Similar thing applies for my VD. So this way you shift your PMOS operation from third quadrant back to first quadrant by by instead of keeping VDD as 0, you shift your source. Instead of keeping VS equals to VGD equals to 0, you give a high positive value to Vs, so that your whole curve shifts to a positive. Now two types of IV characteristics are extracted from a MOSFET. One is output characteristics, one is transfer characteristics. So output characteristics no are are called IDVD, that is your drain current with respect to drain voltage. So for this you fix your gate voltage and you sweep across your drain voltage, and you see how your drain current changes here, and you get some curves like this, where you have a linear regime for small VDS and a constant current for high VDS, which is your saturation regime. And as you change your VG values, your curve increases or decreases depending on your VG values. Next is called transfer characteristics, which is also known as IDVG characteristics, that is your drain current with respect to your gate voltage. In this case, you fix your drain voltage and you sweep across your gate voltage, and you get a curve like this. So this is your subthreshold region below VT, where your current is almost zero, and then post VT you get your curve like this, and you see for small VD you have a linear region, and for high VD you have your saturation region. Next we talk about input and output resistance. So the input resistance, that is the resistance across your gate from your gate, is in the is very high, is in the 10 power 9 to 10 power 12 ohm range, that is tera ohms range, and that is due to your insulating gate oxide in the middle, whereas your output characteristics are calculated. Output resistance is calculated as R naught equals to VDS by VI dVd by dId at certain VG voltage. Then we talk about drain conductance and transconductance. So you on your gate voltage you apply a small AC signal with your drain with your DC bias you apply a small AC signal. So the output current becomes the current from a DC bias and current which with respect to your AC signal which is responding to your AC signal. So when you calculate your resistance, you get so when so you get current back from the operate constant DC bias, and you also get conductance from due to constant del ID by del VGS at constant VD into and del ID by del VDS into at constant VGS. So the AC drain current can be deconvoluted into two cases. One due to constant bias current, and one due to constant gate bias, and then and this results in two conductances. One is your output conductance or drain conductance, which is proportional to inversely proportional to your output resistance, and the other is your transconductance, which is del ID by del VGS. So this is calculated as your slope in transconductance is calculated from your transfer characteristics, and output conductance is calculated from your output characteristics. Now if you put this in your equation, so for linear regime, ID equals to mu Cox W by L VGS minus VT VDS. So if I calculate transconductance here, that is del ID by del VGS here, my transconductance linear becomes mu Cox W by L into VDS. So you can see it is independent in the linear regime. My transconductance is independent of Vg. It only depends on Vd. Then when it come into saturation region, I get Id equals to mu Cox by W by 2L equals into Vg minus Vt whole square. Now if I do my del Id by del Vgs here, my saturation region transconductance comes out to be mu Cox W by L into Vgs minus Vt. So here you can see my transconductance is constant with respect to VDS and increases linearly with respect to my VGS. The MOSFETs are the fundamental building blocks in a digital circuit because they act as an on-off switch. That is, when at low VG, that is at low VG, there won't be any drain drain current, and we can call the circuit as we can call the transistor as in the off condition, that is disconnected condition. And then when my VGS is greater than my threshold voltage, then ID becomes very high, and now this can be called as on condition, that is the connection, my drainer source are connected now. So now we can calculate the ratio between our on current and the off current. So off current in ideal condition should be zero, but in reality, uh, due to leakage across the insulator as well as other quantum effects, my off current is not ideally zero. So we can calculate the ratio between I on and I off, which comes out to be in the order of 10 per minus 4 to 10. It comes out in the orders in around 6, order of 6 to 7, or 5 to something in the order 5 to 7 orders. So you can see here they have plotted transfer addresses ID versus VGS in log scale, where your ID is in log scale. So you can see so this is your threshold. So you can see post threshold you have a very high current, and in the sub threshold regime, current does not instantly go to zero, but reduces exponentially, such that when it reaches at Vg equals to zero, my current is very very low, and this is called my off current. So my off acts as my zero logic as my zero in boolean, and my on current acts as one in boolean logic. And due to this switching mechanism, MOSFETs become the fundamental building blocks of a digital application. So next we talk about subthreshold swing. So as you can see, in the subthreshold region, my drain current is exponentially proportional to my gate voltage. So I can calculate the slope between my log of drain current versus my gate voltage. So I can to get how what is the effect of gate voltage on my drain current. So I can write the equation as I equals to I naught exponential q v vg by nkt, because which is the exponent equation for thermionic emission. Then I write 10 I equals to I naught exponential d q vg plus dv by nkt, which is that is my when my current becomes 10 times at addition of a dv voltage. Now I divide this, I get n equals to exponential q dv by nkt. So this dv is the voltage required to bring one order change in my current, and when I solve this, my this subthreshold swing comes out to be n kt by q into ln 10, which is 2.303. And when you solve this, this comes out to be 60 millivolts. So my subthreshold swing is equals to n into 60 millivolts, and the value of n can be changed from 1 to 1.5 or something like that. So the n can at the minimum be equal to 1. So in our classical MOSFETs can have a minimum subthreshold swing of 60 millivolts per decade. It says per decade because it's the voltage required to bring one decade change, that is one order change in the drain current. So these are different type of CMOS technologies that are employed in making in fabrication of our MOSFETs. So it's called CMOS because it comprises of one N MOSFET and one P MOSFET, that is complementary N MOSFET, NMOS and PMOS. So when they combine, they work opposite to each other, in opposite direction to each other, and due to which they enhance the switching behavior of our circuit. And by working opposite to each other, they act as inverters, which form the basis of all the digital operations. So you see here, my at my NMOS, my the P substrate region is very deep, while my N substrate region is very shallow. Here my P substrate region is shallow and N substrate region is deep. So having a deep region gives a better control on VT because your body effect is less. So the traditional followed is called planar CMOS technology, where you have both deep P wells and deep N wells, and your transistors are separated from each other from something called field oxide. So field oxide acts as insulation barrier between your transistors. This is known as your CMOS inverter. That is a connection between your PMOS and NMOS device. So we have studied that in NMOS the source is connected to a ground, and in PMOS the source is connected to a VDD value. So by doing that, you can apply a same gate voltage to both of them, and due to this, when one is on, the other is off, and when this is so here the when I'm applying a zero, when I am applying a VG equals to 0 here. Now this sees my VG as 0, and this sees my VGS as minus VDD, due to which this one is on and this one is off. So I have a flow of current from VDD to output. I have connected my drain to a common output terminal, and I've connected the gates to a common input terminal. So when I'm giving a zero at my input, the PMOS the PMOSFET is on and my NMOSFET is off. So there's no connection between my output and ground, but there's a connection between my output and VDD. So the voltage at the output is almost equal to voltage here, which is VDD. And when I apply a high gate voltage, that is equal to VDD. This is seeing a gate voltage of VDD, and this is seeing a gate of 0. So this becomes off and this becomes on. That means my output is no longer connected to VDD, it is connected to ground. That means it is now the voltage at the output is equal to 0. So you see, when I am applying 0 in input, I am getting VDD at output. When applying VDD at input, I am getting 0 as output. So this is called inverter, as it is inverting the states between input and output. So when my input is high, my output is low, and when my input is low, my output is high. Now we will do some practice questions. First question: the transfer characteristics for an N-channel MOSFET is given in the figure below. Identify the mode of operation of the given MOSFET in the regions A, B, and C. So this is the figure. Option A: subthreshold saturation linear, linear subthreshold saturation, subthreshold linear saturation, saturation linear subthreshold. So the answer to this is subthreshold linear saturation. So you see my A is at very low VG. So when at low VG my current is 0. This is called subthreshold region. You can see in the B region I have a linearly increasing ID. So this is my linear region. And in my C I have a constant ID with respect to VDS. So this is my saturation region. In a MOSFET operating in the saturation region, the channel length modulation effect causes an increase in the gate source capacitance a decrease in output resistance, a decrease in transconductance, a decrease in the unity gain cutoff frequency. The answer to this is decrease in output resistance. So as VDS increases, the channel length shortens, resulting in increase in drain current, that is decrease in output resistance. Consider an N-channel MOSFET with the following parameters. Conductance parameter kappa equals to 1 milliampere per volt square, and the threshold voltage VTH equals to 0.75 volts. The drain current ID for the gate to source voltage VGS equals to 2 VTH, and VDS equals to 1 volt in milliamperes is 0.28, 4.5, 2.5, 5.1. So the answer to this is 0.28. So if you calculate Vg minus Vt, it comes out as 0.75 volts, which is less than VDS. So this is in the saturation region, and the current in saturation is mu Cox W by 2L Vth minus Vth whole square. This whole thing is called your conductance parameter, which is given to you as 1 milliampere per volt square. So you just multiply everything here, you will get 0.28 milliamperes. Next question. Consider an N-channel MOSFET with threshold voltages VTH operating under pinch-off conditions. Based on the figure, choose the correct condition that indicates the onset of pinch-off. VDS is less than VGS minus VTH. VDS equals to VGS equals to VTH. VGS equals to VTH minus VGS minus VTH. VDS less than VGS plus VTH. This we know VDS equals to VGS minus VTH is the pinch off condition. At this point, the inversion charges at the drain end becomes zero, and there is no more channel for further further current to transfer. For a short channel N MOSFET with P-type silicon as substrate, the critical field at which electron saturation occurs is around 1.5 volt per microns, and the saturation velocity Vsat approximately equals 10 per 5 meters per second. Based on the figure below depicting the velocity saturation, choose the incorrect statement. For lower field strengths, the carrier mobility is not constant. The slope of the region below before reaching critical electric field strength EC represents carrier mobility. The velocity of the carriers tends to saturate due to scattering effects. Velocity saturation effects are less pronounced on electric vehicles. Next question. For a short channel N MOSFET with P-type silicon as substrate, the critical field at which electron saturation occurs is around 1.5. The answer to this would be for lower field strengths, the carrier mobility is not constant. Next question, a silicon MOSFET has the following parameters: Na equals to 10 per 16 per centimeter cube, Tox equals to 12 nanometer, epsilon SiO2 equals to 3.9, epsilon Si equals to 11.7, and phi F equals to 0.3473 volts. The body effect coefficient gamma is dash 0.1, 0.2, 0.4, 0.6. So the answer to this is 0.2. So gamma is calculated as square root of 2 q epsilon Si Na upon Cox. So Cox you can calculate by epsilon ox by Tox, and 2q Na epsilon Si Na you can calculate from the given values. So all this gamma will come out to be 0.2 root volts. The sub-threshold swing is defined as decrease in gate voltage necessary to increase the drain current by a factor of 10. Increase in gate voltage necessary to increase the drain current by a factor of 10. Decrease in drain voltage necessary to increase the drain current by a factor of 10. Increase in drain voltage necessary to increase the drain current by a factor of 10. So the correct answer is increase in gate voltage necessary to increase the drain current by a factor of 10. What is the main purpose of P-channel MOSFET in a CMOS inverter circuit? To pull the output to ground when the input is high, to provide a constant current source, to pull the output to VDD when the input is low, to invert the signal. So the answer to this is to pull the output to VDD when the input is low. The ideal long channel N MOSFET and P MOSFET devices shown in the circuits have threshold voltages of 1 volt and minus 1 volt respectively. The MOSFET substrates are connected to their respective sources. Ignore leakage currents and assume that the capacitors are initially discharged. For the applied voltages as shown, the steady state voltages are V1 equals to 5 volts, V2 equals to 5 volts, V1 equals to 5 volts, V2 equals to 4 volts, V1 equals to 4 volts, V2 equals to 5 volts, V1 equals to 5 volts, V2 equals to minus 5 volts. So the answer to this comes as V1 equals to 4 volts, V2 equals to 5 volts. An NMOS transistor operating in the linear region has ID equals to 5 ID of 5 microamperes at VDS of 0.1 volts. Keeping VGS constant, the VDS increased to 1.5 volts. Given that W mu n Cox by L equals to 50 microamperes per volt square, then transconductance at the new operating point in microamperes per volt is 40.7, 45.2, 52.5, 60.3. So the answer comes out to 52.5. So for linear region, the current is given as mu Cox W by L, VGS minus VTH, VDS into VDS. From this, you can calculate VGS minus VTH equals to 1.05 volts. So when the current is VDS is 1.5, it becomes saturation region, and the saturation region transconductance is given as mu Cox W by L VG minus VT, which you can solve using the equations given, and it comes out to 52.5 microampere per volts. So that is all for today. Thank you.